All right, good morning. Fiber optics topic today. Fiber optics topic today. All right, August 31st, last day of August, and tomorrow would be, sorry, July 31st. Tomorrow is August 1st. I'm a month ahead. So this is week 12. We get week 13 and 14, and during the week 14, I'm going to give you the last test and that should be fine. So we have this fiber optics topic this week, and it says on the thumbnail, it says it's going to say that it is part one. Well, for all the people of the whole world that just can't wait to see my videos, there will be no part two posted on the net for this year because the class is in person tomorrow. Okay, cool. So let's start. Fiber optics is the topic of today. Now, you see this thing here is spelled F-I-B-E-R. You're going to see once in a while the other spelling, F-I-B-R-E. These two are going to be exchanged. And for the longest time, I was trying to establish the correct spelling, looking at some literature and all that stuff, and I couldn't make sense out of it. Sometimes you're going to see that thing spelled one way, and sometimes you're going to see the fiber spelled the other way, and there seems to be no rhyme or reason where the literature comes from and who it is written by. In fact, even some of my writings on this include both spellings because I myself can't make up my mind which way I want to spell this one. So that's that's as far as the spelling of the fiber optics, or otherwise known as optical fiber. Right, first slide. Okay, come on. Click on me. There we go. All right, what do we see here? We see the effect of something that's popularly called as a rainbow. Rambo? No, that's the other thing. Rambo was a tough guy. This is a rainbow, right? All right, what do we see here? We see a light frequencies broken into their basic elements. Now, this part that we see here, from that purple on one end, purple colors on one end, that purple kind of disappears into the red on the other end, and that red sort of disappears as well gradually. This is the light spectrum that is visible to, this is the visible spectrum of light. Visible, what do I mean by visible? Visible to us humans, all right? So what's with the light frequencies, visible light frequencies? Well, we humans see this part of the frequency spectrum and this part of the light spectrum. Does it mean there is no light beyond this point? And does it mean there is no light beyond this point? No, there is actually light beyond this point. We just can't see it. Some animals, though, they can. So, for example, things like animals like hawks, turkeys, eagles, all those prey birds or birds of prey. They see a little bit more colors here towards that invisible to us, violet, ultraviolet. So the turkeys and eagles and all the birds of prey see a little bit more towards that. Other animals such as dogs or deer, they see a little bit more towards that end, more than us. Do you ever throw a frisbee to a dog in the late evening to the point that we can't see, and the dog just runs after the frisbee and catches that in the air? That's because dogs can see a little bit more of infrared. So what is invisible to us, it is kind of, it's just like the black and white security camera, you know. So animals see colors in a different way. Bees, I think bees see more towards ultraviolet. So the colors that we see, green grass, blue skies and whatnot, they seem completely different. If you would just put kind of a color translation, the different species of us being on the planet see things in a different way, and there's a purpose of that. So sometimes because you could see more detail one way or the other, and the purpose of your existence. Like for example, animals that walk at night in the woods, they see more towards infrared, so they can see. Right? All right. So that's how light is. Now, this is when you shine a light towards some sort of a medium which is going to be able to break the colors. So how do you see that rainbow effect? You would have to have two conditions. One, it has to be raining, so the light has some kind of a medium to pass through, and which will be water. And the sun has to be visible at the same time. So rain and the sun at the same time, not behind the clouds. And what do? You just face the sun, and you're going to find the rainbow right behind you. All right. So how is this happening here? It's because of something that is called index of refraction or refraction. What is a refraction? Well, if you shine a light straight into the interface. So, what's an interface? Here is a medium number one. A medium is a substance through which something travels, to which something utilizes. So in this case, we utilize let's say, for example, this is air, yeah, and let's say this is some other medium such as, well, let's say glass. All right, so in the glass, light will travel slightly slower than in the air. If you shine the light straight perpendicularly to the interface, and the interface is that point where one medium meets the next, so that's the interface line. And if you shine the white light straight into it under the right angle, so here would be right angle, then you would not have the frequencies break into different you would not have the main frequency or all the frequencies, the white light, you would not have that light broken into different frequencies. It would still be white, but it would just slow down a little bit accordingly to how the glass slows down a little bit more than the air slows down the light. But if we're dealing with an angle, then it depends on what the angle of incidence is from the normal, and we will talk about that in the next couple of slides. The normal is the line perpendicular to interface. So it depends on the angle you shine the light on. You have, well, different possibilities. First, if it's the perpendicular angle, we established that the light would still be white, but it would just slow down a little bit. Now, if you shine at a certain angle, well, three things could happen. The light could reflect, which means bounce off the interface and go this way, just bounce off of it. Or it could refract, so bounce off would be reflection. It would reflect and come back on the same side. Or it can cross the interface, which we would call that would be refract. Instead of reflect, it would refract, which means that it would still pass through, but not at the same angle and it depending on the differences of something that's called refractive indexes of those two mediums, the light would take different angle, one way or the other, and more or less. Now, notice one thing here. How is it happening here? Which frequencies, because in light, the frequencies are being expressed in colors, same as with sound. Sound also has different frequencies. It has lower frequencies and it has high frequencies, right? So we distinguish the frequencies by hearing the pitch of the tone. Now, when it comes to light, we distinguish the frequencies by, well, different colors. Now, never mind for now which are higher frequencies and which are lower frequencies. Which do you see, or the colors are being affected more or less? Which means when you pass the light through the interface, those will bend. The travel, the direction of the travel of those frequencies or the colors is going to bend. Some of them are going to bend more and some of them are going to be bending less. This is important when dealing with fiber optic transmission signals. I'm getting at something here, right? So which colors are being affected more? Which colors bend more and which colors bend less? You can say it on voice if you wish, or just type in the chat line. I just want to see that if you're paying attention. So please, somebody speak up, say something. Which of the colors are being affected more by bending more and which are bending less when it comes to the direction of the travel? Come on, somebody say something. I'm going to have a sip of my coffee, which is getting cold now. Red and orange, yellow band more. We got one. Or is it the other way? See, here's which is more, which of the frequencies travel closer to this direct? The other way. Yeah, there we go. Yeah, other way towards violet. Yeah. There you go. So the red ones are straighter than the purple ones. The purple ones. All right. Okay. So it just so happens that the red color is the lower frequencies and the purple colors are the higher frequencies. We'll look at the table here. Why is this happening? Okay, well, if you, let's say, I'm going to digress a little bit, but I'll do it with purpose. If you see a little guy, let's say, 5 years old, walking down the street and meeting a guy who's like 40 years old, do they have something common to talk about? Well, not much, really. The older guy could say, "Hi, this is, hi, Billy, nice baseball cap." "Oh, thank you, sir." And they go their own way. So that's as far as the conversation can go. Are they going to talk about toys or cartoons that they like? No, because the interests of the older guy are completely different than the interests of the younger guy. So they're not going to spend much time on conversation. But let's say if there is the one little guy meets another little guy, and they're going to say, "Oh, hi, how you doing? Did you see the cartoon? Last night? Did you see this? Did you? How about? Look, let me show you some of my toys that I got." So they're going to have a little bit more conversation. So that's what happens here. The red colors are the higher frequencies. Sorry, the lower frequencies, longer wavelengths, and they seem to be affected less by the glass. They don't hang around for they don't want to talk to anybody. They just keep walking. Now, here are the purple ones, are the higher frequencies, shorter wavelengths, and those wavelengths are closer to some of the particles that make up the glass, and they seem to be interacting with the glass particles a little bit more. So they stop a while and have a little conversation. So that's what slows them down. Not really conversation, but it's just a bit of an analogy that I'm presenting here. So you can see the higher frequencies are affected more, which means they are distorted more. The lower frequencies towards the red. Now, is there light beyond red or below red? Yes, there is light below red. We just can't see that, but those frequencies below red, they are also called light frequencies. We just can't see them as humans, but it's still light. So they are not affected as much. They pretty much almost go as they are. They are affected a little bit, but not as much. So they are distorted less, which means they can probably travel further, which means probably they are not going to lose as much energy along the way as the purple ones. So that's one good thing to remember. All right, let's go to the next slide. As far as the calculations, and this is something I'm not going to test you on. However, I would encourage you to investigate further because it's a nice thing to know. In this course, we just are going to brush against the idea. So anything beyond is not need to know, but it's nice to know. But there's a fine line between nice to know and need to know. So, calculations. Wavelength is measured in, It's measured in meters. That's our convention. And the symbol of the wavelength is that little Greek symbol that's called lambda. Right? Now, frequency, when it comes to light, it's a Greek symbol that's called nu, like the new. I got new car, new. And it looks like our alphabet letter V, but in Greek it's actually pronounced nu. Take it from me. Actually, don't. I don't know any Greek. I know some Greek people, but I don't know any Greek language. But I know that this is lambda, and I know that this is nu. There you go. You gotta start somewhere, right? And it is measured in whatevers per second. Usually it would be cycles per second. Speed of light, here's that. And here's that letter C. Now, is this pronounced in Greek something else? I don't know. But that's the symbol of speed of light. And it's measured in meters per second. Right. Now, the relationship between frequency and the wavelength and speed of light is as such. Here's the triangle. And here the frequency equals speed of whatever it is speeding by its wavelength. Now, here is the speed of light, which is 3 times 10 to the 8th meters per second. That's fast. All we have to know, that's really fast. We will never be able to do that. Although some people on Star Trek, who watch Star Trek, might argue that maybe we will be able to do that. Look, they go warp 9, which is 9 times speed of light. Okay, that's a movie. Now, sometimes you're going to refer to this formula, frequency equals 1 over period. But when I show you those tables of frequencies versus the wavelengths, if you blink, you're going to miss it. But if you have investigative mind, you're going to put that, or inquisitive mind, you're going to put that to a test, and it's not going to calculate. Because we are dealing with the moving wave, not a stationary vibration. So when you're working with your function generators, and if you want to calculate the frequency, you just have to find the period of it, and you just reverse that. Well, reverse that. You just flip it over, and you get the frequency, and then we got the period. Right? Well, that's why. So here are some videos. If you want to investigate further, I would encourage you to do so, but I'm not going to test you on this. It's just so. You go, if you look at this table here, all right, and you put that frequency over 1 over a period and try to get the frequency, or vice versa, that's not going to work here. All right. Now, let's go back to the next slide here. Here is the, well, light spectrum, or the frequency spectrum. Over here, okay, so we have very high frequencies. These are the gamma rays, and then some lower frequencies will be the X-rays, and then we hit the light. And we have part of the human, invisible to humans, light, and then we hit the ultraviolet, which would be above violet. And then we see the colors. See, that's a very narrow spectrum here that we can actually see. And then we hit the red, and we can see here, we see we reach all the invisible to us light, but it's still considered to be light frequencies, and those will be the infrared, under red, all right, or less than red. And then you have the radio frequencies, and later on you're going to have some sound frequencies and so on. So there's, everything vibrates. The whole universe vibrates. We are able to exist because of vibrations. And there are some different theories, what exists, what it doesn't. We're not going to get into it. But, well, remember when we saw that the red frequencies, red colors, are being affected less, which means they can pass more easily through the glass, and the violet ones are affected more, which means that they are distorted more. They were going to be slowed down more. So why, it would just make sense, if you want to transmit signal as comfortably as you can, you're going to use the frequencies that are affected less, that can pass through easier. Excuse me. Sip of coffee. Talking too much. Teacher's syndrome. So we're going to use those red frequencies to pass through the glass, so we can be as efficient as possible when transmitting signals. And so here are the colors, and here would be the wavelengths. Now, fiber optic communications, typical wavelengths. It would be, well, the visible light is more or less between 400, somewhere here, and 750 nanometers, somewhere here. See, that's our visible light. And notice that when it comes to fiber optics terminology, yes, we could express the light in frequency numbers, or we can express them in wavelengths, and it just so happened that it can stay that way, that we are expressing the light colors in wavelengths. It just so happened. So between 400 and 750 nanometers, more or less, that's the visible light to us humans. Now, typical wavelengths used for transmission would be 780 nanometers, 850 nanometers, 1310, 1550, and that's pretty much it. Okay, let me go here. Why is that? Why don't we transmit? Okay, so here's 780 nanometers, so somewhere here. And the next one will be 850, so it would be somewhere here. Are we going to transmit somewhere on 820? We should, right? But we don't, and there's a reason for it. And we'll talk about that next time we see each other. It's actually called water bands. Why don't we transmit there? Because the light just disappears completely when we are between those. We'll talk about that a little bit further. Right? But these are the typical carriers. What is a carrier? Well, just like the radio frequencies, we have carriers, like for example, Jack 102.3 FM. That 102.3 is 102.3 megahertz. And that is the carrier. And carriers are used to tune the transmitter, transmission band, and the receiver listening band. So when both are tuned to each other, they lock onto each other. They actually see each other. Actually, the receiver sees the transmitter. The transmitter just transmits when it comes to radio broadcasting, and the transmitter doesn't care who sees him or her, whatever it identifies as. But the receiver cares what they see. So if I want to listen to a certain station, I'm going to tune my receiver towards that particular radio station. So same thing, so I'm going to tune to the carrier of 102.3 FM or 102.3 megahertz of a radio frequency. Same thing with the transmitter and receiver when it comes to optical fiber. All right. So these are the typical. Now, as the technology progresses, because we humans are such unsatisfied beasts, we always want to strive for something better. We always want to get more comfortable. We always want to get more efficient in things. Is it possible to transmit between those? Yes, right now it is possible. The technology got that far, but still, when it comes to the commercial availability, these are the frequencies for the most part. If you want to get some special, very, very special circumstances, yeah, maybe, but not yet. These are the frequencies that are being used for transmitting and receiving signals through optical fiber. All right. See, here's the table of the colors, and I was talking to you about the formula. There you go. Violet goes between 380 and 450 nanometers, and that translates into between 668 to 789 terahertz. All right. How many zeros is tera? Well, you find out. And so on. I'm not going to read that thing, just so you can see. Well, what can we see here? Well, this you can see that the violet frequencies are higher number frequencies. When we travel towards red, going through all the colors, is that red is lower frequencies. So this would be the high frequency light. This would be the low frequency light. Okay. Now, wavelengths is inversely proportional. So the longer wavelength, the higher, longer, bigger number of the wavelength, smaller number of the frequency. That's inversely proportional. So the higher frequencies are going to have shorter wavelengths, and the lower frequencies are going to have longer wavelengths. And this frequency is expressed in terahertz, and the wavelengths are expressed in nanometers. And here's the prism. Does it remind you of any sort of a musical band? It reminds me of something. Oh, yeah. All right, so here's the concept of refraction, reflection, index of refraction, and total internal reflection. Let's take a look at some of those. And video, right? When you download it, you can look at the video and get delighted with all the wonderful things that are being presented there. All right, so index of refraction. The index of refraction, here's the basic formula. It's expressed with the letter of n, and over here we have the speed of light in the vacuum, which means speed of light in, well, nothingness, nothing to slow down, and speed of light in something, whether it be glass, water, or other elements. Of course, the speed of light in the vacuum is going to be the fastest. And whenever you are going to transmit light through anything else than a vacuum, and vacuum is basically nothingness. So if you transmit the light through somethingness as opposed to nothingness, well, that somethingness is going to slow the light down. So the speed of light through something is always going to be slower than with the speed of light of vacuum. Okay, all right. Now let's talk about something that's called a refraction. So here is air, here is glass. Here is air, here is water. What can we see here? Okay, so here is glass, here is air. Or we can say vacuum. But let's call it air because it's easier to imagine air than the vacuum. All right, so here is the interface, and here is the normal line, which is perpendicular to the interface, and here is the angle at which the light enters the interface, hits the interface. And both of them are the angle of incidence, light coming in. Both of them are, let's say, 60 degrees away from the normal. Now, what happens here? In glass, the light is going to puncture through the interface, and it's going to bend a little bit here. Or is going to have the angle of refraction of 34.5 degrees. Now, when we do the same thing with water, the light bends in a different way. It bends a little bit. Can you see that it bends a little bit less in water? Because the glass and water have different indexes of refraction. They have different n's. And then when it leaves, it enters, that it corrects itself back to whatever it was. All right. All right. Here's another example. Here is one medium. Here's another medium. So this one, let's say it's air, and this would be aqueous medium, which we can call water. And we have the light traveling from water towards air. Water slows the light down, which has a higher index of refraction, or higher refractive index. There is a reason why because we are working ourselves towards the fiber, what's happening in fiber optics. So there's a reason why we're shooting the light this way now. All right, so this here, medium, water, we're going to say it's less pure to travel in than in the air. There's more obstacles here to go through in the water for the light than it's in the air. The water is a denser medium, more dense than the air. Light will travel slower in water than in air. When we shoot the light, depending on what the angle is between the angle of incidence here from the normal, if we shoot it at certain angle, the light is going to reflect and will be contained on the side of the interface. It will not leave water. It will stay in water. It will stay within this medium. Now, when you start increasing the angle or decreasing the angle here, depending on which side you're looking from, you go towards the normal. You're going to have a sharper angle here. You're going to accomplish the phenomenon that the light will not have the ability to reflect. It will puncture through and it will go on to the other side. Now, the angle at some point between reflection effect and refraction. When we're dealing with refraction, the light punctures through or punctures the interface and it goes on the other side. That's refraction. When it stays within the medium and it just bounces off the interface, it's called reflection. There is one point you're going to reach that the light will travel just on the interface, and it is called a critical angle. All right. Well, one important thing to remember about this slide is that, yes, it is possible to keep the light within water, which is less pure than the air. It has higher index of refraction than the air, less pure, slows down the light, keeps the light in. Lower index of refraction doesn't slow the light as much, purer or less dense than this medium here, which is water, and light travels faster. All right, got that? We're getting somewhere with this. Some of the facts to consider about the index of refraction. Speed of light is this big number. Now, the speed of the light in whatever other than a vacuum is always going to be slower. So, when the speed of light in the medium decreases, then the refractive index increases. Materials with higher index of refraction slow the light more. Okay. Now the index is going to be, let's say we consider this, let's say get this thing 1, and it's going to be less than 1. Right? Is it going to be less than 1 or is it going to be more than 1? This is 1 over something less. 1 over something less. Right? I will leave that with you. All right. Here comes the next slide. All right. Material. Speed of light in a vacuum. Light traveling through air, not the speed. Light traveling through vacuum, air, water, ice, glass, and diamond. Just a couple of examples here. The index of refraction is 1 because 1 over 1 equals to 1. 1 over something less in the air is going to be 1 and little something, a little bit more than 1 at the index, right? Water slows down even more. Oh, the index of refraction is going to be bigger. Ice and Right? What does it tell us here? The index of refraction is never going to be less than 1 because this is the border here. That's the limit. It's always going to be bigger than 1. Yep. All right. Here is how the signal transmission works in fiber optic strand, in the strand of a fiber optic line. Here is something that's called a core. And here's something that's called a cladding. Cladding is another word of surrounding, enclosing, hugging. All right. The light has to travel in core. Remember this slide right here? We want to keep the light within the core. So let's say this is the core and this is the cladding. The core is going to be slightly less pure of a glass than the cladding. Cladding will have a purer glass than that. Normally you would think, because we want to keep the light travel in core, so let's make that core more pure than the cladding. No, it's actually the other way. Right? Because what we want to achieve is something that is called total internal reflection. We want to achieve the total internal reflection within the core in order for the signal to travel within the core, because that's where we want to keep it. We are injecting the signal into the core on one end of the fiber, and we want to retrieve the signal on the other side of the core. Otherwise, what would be the point? If we didn't achieve the total internal reflection, or something as close as possible to total internal reflection, the signal would escape. So we wouldn't be able to catch the signal on the other side, right? So the fiber optic line transmission happens thanks to the phenomenon that is called a total internal reflection. And that's how we are able to transmit and receive signal in fiber optics, which means here's the core and here's the cladding. The cladding is an extremely, extremely, extremely pure glass. The core is also extremely, extremely, extremely pure glass, but on purpose it's made a slightly little bit dirty. It is doped with something to slow the light down ever so slightly, and when that happens, we are going to have the interface between the core and the cladding, which if you were able to shrink yourself into one little person like that you could walk in there, walk through the glass, you would find yourself in a huge tube that would look like a mirror. Well, mirror reflects, right? So the light, now we're going to have to make sure that the angle of incidence or the angle of insertion is of a certain angle and no more, because we want to keep the light in. If we shoot the light at this angle here, the light actually escape. In fact, if you bend the fiber, because you can, if you bend the fiber too much, then some of the lights are going to hit that interface here at the higher angle because you bend the fiber, and some of the light is going to escape. So we want to avoid any kind of distortions or bends, and we distinguish two types of bends. There's a macro bend and there is a micro bend when it comes to lights, to optical fiber. A macro bend is bigger than the micro bend. A macro bend is that, well, you have to run a fiber optic line and you have to run it around the corner. So you have to turn a corner somewhere because you have to. And that would be called a macro bend. And you want to make that angle, the radius of the bend, as gradual as possible. And you don't want to exceed certain angles, right? So the light doesn't escape. Macro or micro bend, which is the smaller, is if a fiber is being pinched by something. Then you get a micro bend like this, very small. And those are really bad because then the light starts reflecting, and sometimes it will prevent enough that the transmission is going to fail. Right? So the micro bands are a really big enemy of fiber optics. Now, before we let you go, we continue that tomorrow in person. We distinguish two types of fiber for commercial purposes. We have something that's called a single mode fiber and a multi-mode fiber. Notice that the core, or the cladding size is the same, and it is 125 micrometers, the size of the cladding in both cases. The cores are different. The core in a single mode is tiny, small enough. Well, it's about 9 micrometers or 9 microns, same thing. It can go down, some of them produce as low as 5 microns. And it shoots or transmits a single mode of light. What is a mode? A mode is the stream, light stream. If you have a light bulb in your ceiling, just a regular old-fashioned tungsten light bulb, you're going to see that the light bulb is producing light in all directions. So you're going to have all angles transmitting. So these are those angles, those light streams are mode. And it's infinite number of modes. So some of the modes here are drawn in the multi-mode, but it doesn't mean that there's only 1, 2, 3 modes traveling. There's infinite number of modes here. And some of the, but for the purpose of simplicity and be able to explain things, we just draw a few of those just to get the concept. Now, some of the light enters at this angle and bounces off and travels down the pipeline. Some of them are going straighter and they travel this way here and so on. So you can see that some of the light beams or light modes are going to get faster or quicker to the end than some of the at a different angle. So that's why when we have a sharp signal at the transmission end, that signal at the end is going to be slightly more like muddy or dispersed, not going to be as sharp. That's why the multi-mode fibers are being used for shorter distances And the single mode fibers are being used for longer distances. This, depending on different sources, and different sources will give you different numbers, anywhere from 800 meters to 3 kilometers. That's a big span from different sources. So, but let's say up to realistically a kilometer and a half, for example. So that would be the short distance. Well, remember, copper, 300 feet, kilometer and a half, that's still much longer, right? Much farther. Now, this fiber optic single mode optical fiber, longer distances. Different sources, again, will tell you different numbers, but you're talking in tens of kilometers. Some of them will tell you that 10 kilometers is the limit. Some of them will tell you that 100 kilometers is the limit of that. We'll continue on when we see each other tomorrow in person. All right? Because, well, it's 10:54 right now. You still have to have time to do whatever and get ready for the next class, and so do I. All right. Thank you so much, and I'll see you when I see you. You guys are all wonderful, but not as wonderful as me. All right. Thank you, guys and gals.